Hello, and welcome back to Shine Sleep Stories. Tonight, we're going to an extraordinary place, so far away that the light emanating from it right now will wait 700 years to reach your eyes. We're silently making our way through soft black space past the pale blue glow of our own little Earth, the warm amber mist of Jupiter, the frozen silence of Neptune, and the long, dark expanse beyond. We're going to meet a star. Not just any star, not our own simple, stable sun, however pleasant and reliable it may be. No, tonight, we're going to visit something whose dimensions are almost incomprehensible, something very ancient, something burning with a slow and terrifying beauty, on the verge of being a star. We're going to meet Betelgeuse. Close your eyes if you like. Let your body sink deep into the surface that carries you. Feel the weight of your limbs. Notice your breath slowing. Feel your thoughts begin to scatter like dusty pink particles dancing in the midday light. There's nothing you need to do right now. There's nowhere you need to go. The world outside can wait. All that exists tonight is this journey. You, the stars, and the vast silent darkness between them. Let's begin. Imagine for a moment that you are weightless. You are floating somewhere above the world so high that the layer of air beneath you has become a thin blue thread, like a delicate watercolor stroke curving toward the planet's horizon. Below, you can see the clouds slowly swirling above the ocean. You can see the wrinkled darkness of the mountain ranges and the silvery thread of the great rivers. Everything is silent. Everything is calm. You don't feel cold. You're not afraid. You're just suspended here in the gentle darkness, looking down at the world you came from. And then, very slowly, you begin to move. Not fast at first. Just as if you were gliding on the surface of a warm lake, and given the gentlest propulsion, you spread out gently. The world beneath you shrinks. The blue thread of atmosphere thins and disappears. The sun shines on your left, white and magnificent. Smaller than it appears from the ground, yet terrifyingly bright in the darkness. Around it, stars appear. These aren't the pale, scattered diamonds you see on an ordinary evening. Not the faint glimpse of the Milky Way on a good country night. No, here, far from the last vestiges of atmosphere and light pollution, the stars are everywhere. They are as dense as salt poured onto a dark cloth. They fill the sky in every direction, above, below, and to the sides. There is no above, there is no below. There is an endless ancient sphere of light surrounding you on all sides. And the silence is so complete and perfect that it almost feels like a presence. You glide. The sun is now behind you, shrinking. But you are passing through the asteroid belt, a giant ring of slower rotating rocks, each capturing distant sunlight in its own unique way. Some gleaming like silver, some dark as coal, some reddish-brown, patiently spinning in this cycle for 4.5 billion years and expecting to continue for another 4.5 billion years. Beyond the asteroids, Jupiter begins to appear. It's so enormous. Even from here, it's the largest thing from your perspective, other than the sooner vast sphere in amber, cream, and rust-colored bands, its famous storm, like a rotating eye that has watched over the solar system for centuries. Its 4 massive moons hang around it like children circling a parent, each a world of its own, each filled with a cold secret. You glide past it. Now Saturn appears, and even if you've seen its pictures, even if you've known it existed your whole life, reality still catches you off guard. Those rings, like the brim of the world's most elegant hat, they stretch outward from the planet's equator, billions of them. This structure, built on millions of ice and rock fragments, each moving in its own orbit, forms such a thin shape relative to its width that if you were to shrink it to the size of a piece of paper, that paper would be more than a mile wide. You leave Saturn behind. You pass Uranus, its pale blue-green hues and tilted position, orbiting like a slow upside-down ball of rock, unsteadily spinning from the impact of an ancient collision. You pass Neptune, a deep blue and stormy planet, spinning in such darkness so far from the sun that it appears here only as the brightest star in the sky. And then you leave the solar system entirely. Now before you lies interstellar space, the vast emptiness between stars, Of course, this space isn't entirely empty. Here and there, hydrogen gas and coal dust particles drift in the darkness. Occasionally, you pass through regions that are slightly denser and slightly warmer, but mostly, it's a profound void stretching in every direction, filled with distances that defy imagination. The closest star to our Sun, Proxima Centauri, is 4.5 light-years away. This means that light, the fastest thing in the universe, traveling at nearly 300,000 kilometers per second, would take 4 years and 3 months to traverse this distance. If you were to drive a car at highway speed toward Proxima Centauri, it would take about 50 million years to get there. But you're not driving a car. You're drifting along this impossible distance in the calm current of your imagination. So the journey neither takes nor feels time. You're experiencing every moment simultaneously. Stars drift around you, each as its own sun. Each surrounded by its own invisible planets, asteroids, comets, and cold, dark objects, too small to see from here. Some of these stars are smaller than our Sun. Tiny, cold red dwarfs, burning their fuel so slowly and carefully that they will still shine even when the universe is 100 times older. Some are similar to our Sun, yellow-white, middle-aged, reliable, and stable. Some are hotter and bluer, burning fast and bright on the cosmic timescale, destined to fade in the blink of an eye. And some are something else entirely. Some are giants. Some are giants, in one corner of the Orion constellation. There's a spot you've looked at countless times before but never knew what you were looking at. A star shines there, emitting a distinct reddish-orange light. If you have a good vantage point and have been attentive, you might have noticed it. If you imagine Orion as a figure looking down at you, this star is located on the hunter's upper left shoulder, although its color appears faint from Earth. There it is a warmth, a hint of gold, creating a different impression from the blue-white glow of Rigel or the cool white of the belt stars. This star is Betelgeuse. Its name comes from Arabicate al-Jawza, roughly meaning armpit of the middle. Perhaps not very impressive for something so extraordinary, but there it is. People have been watching it, naming it, and thinking about it ever since they looked at the sky and wondered about anything. And you can understand why they keep returning to it. Even from 700 light-years away, Betelgeuse is one of the brightest stars of the night. Its place is among the 10 brightest stars, and it emits between 100,000 and 150,000 times more light than our Sun. Depending on the phase of its slow fluctuations, on some nights, when its outer layers expand a little more and conditions are right, it is the 7th brightest star visible from Earth. On other nights, it dims a little, becomes slightly darker, and recedes. It breathes. That's the most striking thing you learn about Betelgeuse. It doesn't have the constant brightness of small stars. It fluctuates. It expands and contracts. Its outer layers slowly swell outwards, then retreat again. This process takes place over months, years, and even decades. Much like the chest of a giant sleeping in the dark, rising and falling, which, in that sense, is exactly what it is. Betelgeuse is a red supergiant star. The word supergiant is not an exaggeration. This is a technical classification and refers to the category of the largest stars found in the observable universe. Even within this classification, Betelgeuse stands out. Its diameter is estimated to be between 700 and 1,000 times that of our Sun. Depending on how the outer boundary is defined, it should be noted that this is not a simple question for such a star. Let's try to make this concrete. Our Sun is about 1.5 million kilometers in diameter. That's a truly extraordinary number, far beyond the reach of any ordinary understanding. If you lined up balls the size of our planet side by side along the Sun's equator, you could fit about 109 of them. The Sun is truly massive. Now imagine something 700 times that size. If Betelgeuse were placed in the Sun's place, its surface would extend far beyond Mars' orbit. In fact, it would completely swallow Mercury, Venus, Earth, and Mars. All 4 of the inner planets would be incorporated into the star's mass. Its outer boundary would perhaps lie near the asteroid belt, or even further. Some estimates suggest it would be closer to Jupiter's orbit. You would be inside it. Betelgeuse's surface would be directly above you. Every time you turned your eyes, you would see the interior of a red supergiant star. There would be no outside, just the star. This is an image almost meaningless to the human mind. The mind hasn't evolved to process such scales, but it's real. It exists. Right now, 700 light-years away. Breathing silently in the darkness, there's a star glowing with amber light. This star, expanding and contracting, is patiently and majestically approaching the end of something that has existed for a very long time, exhausting its last nuclear fuel. So, how did it get here? It all begins with a cloud. Asterisk, not like the clouds drifting past your window, not made of water droplets or ice crystals. This is a molecular cloud, a large, diffuse mass of gas and dust floating in interstellar space, composed mostly of hydrogen and helium, with small amounts of carbon, oxygen, nitrogen, and other elements, all in molecular form, all extremely cold, usually only 10 or 20 degrees above absolute zero. Asterisk, these clouds are enormous. Some stretch hundreds of light-years in every direction. They aren't dense by any Earth standard. The gas within them is far sparser than even the best vacuum on Earth. But even with such sparseness, they are large enough that their total mass reaches a significant value. Some molecular clouds contain enough matter to eventually form millions of stars, like our Sun. Asterisk, for millions of years, sometimes billions of years, these clouds simply drift. Then something disturbs them. Perhaps a shockwave from a nearby supernova, the death explosion of another star, passes by. Perhaps the clouds collide. Perhaps the gravity of a passing star or galaxy has a slight effect on the cloud's equilibrium. Whatever the reason, something upsets the balance. A region of the cloud begins to contract. Asterisk, gravity pulls inward. Gas and dust clump together. As they clump together, they heat up, like when you rapidly compress air in a bicycle pump. The center of the contracting region becomes denser and hotter. The rotation in the cloud, the almost imperceptible slow rotation that every large object in the universe possesses, accelerates as the cloud contracts, like a figure skater spinning faster when they pull their arms inward. Asterisk, the contracting core becomes It's not yet a true star. It can't perform nuclear fusion. It's just a hot ball of gas still contracting, heating, and accumulating mass. Around it lies a disk of remnant gas and dust, from which over millions of years planets could form. Asterisk, but the protostar continues to contract. The core continues to heat up, and when the temperature in the core reaches about 10 million degrees Kelvin, something extraordinary happens. Hydrogen atoms begin to fuse. Asterisk, under the immense pressure and temperature in the protostar's core, hydrogen nuclei, protons, stripped of their electrical charge by heat, collide powerfully enough to overcome the electromagnetic repulsion that normally separates them. They fuse, 2 protons form a nucleus, then another proton is added, then another. Step by step, through a chain of nuclear reactions, 4 hydrogen nuclei transform into a helium nucleus. And in this process, a very small amount of mass is converted into energy. Asterisk, not much. The transformation of 4 hydrogen nuclei into 1 helium nucleus releases only about 0.7% of the original mass as energy, but the universe contains a vast amount of hydrogen, and stars are subject to immense pressure and temperature. Therefore, these reactions occur trillions of times every second. And the total energy released is enormous. The star is shining. For the first time, its collapse is halting because the external pressure of its nuclear energy production is being balanced by the internal gravitational pull. The star is stabilizing. It's entering what astronomers call the main sequence, a long, stable, and midlife phase of a star's life where hydrogen burns continuously and steadily in its core. This is where our Sun is now. We're in the middle of our main sequence life. The Sun has been boiling hydrogen for 4.5 billion years. And this process is expected to continue for about another 4.5 billion years. But Betelgeuse is different from the Sun. Betelgeuse was born as part of a much larger gas cloud. It has amassed far more mass. The exact amount of mass it has amassed cannot be determined. Estimates range from 15 to 20 times the Sun's mass, with some models suggesting it was initially larger and lost mass over time. But whatever the exact figure, the logic is the same. Betelgeuse was born with a large mass, and large stars lead quite different lives. Asterisk, a star's luminosity, the rate at which it consumes its fuel, is not linearly related to its mass. It increases much more rapidly. A star twice the size of the Sun isn't just twice as bright, it's several times brighter. A star 10 times larger isn't just 10 times brighter, it's thousands of times brighter. A star 20 times larger consumes its fuel at such a rate that its lifespan, compared to smaller stars, is measured in millions, not billions of years. Betelgeuse perhaps spent 8 to 10 million years as a main sequence star, a fiery, blue-white luminous object burning its hydrogen profusely. Then, the hydrogen in its core began to run out. The balance that had lasted for millions of years began to break down. Asterisk, when the hydrogen in the core of a massive star begins to dwindle, things get complicated. The core can no longer sustain nuclear fusion at the same rate. The external pressure decreases. Gravity gradually gains more space. The core begins to contract, but this contraction heats the core even more. And in the layer of material surrounding the core, which still contains hydrogen, the increased temperature ignites a new wave of fusion. This layer begins to burn hydrogen around the depleted core, and it does so much faster. Though not as fast as the core did before, asterisk, the extra energy is pushed outwards. The star's outer layers, the envelope, expand. The star grows. As it expands, the opposite happens. Although the star produces more energy in its interior, it cools as the outer layers expand. The surface temperature drops. The star changes from being hot and blue-white to a cooler, orange-red color. Asterisk, the star is now a red giant. For our Sun, this will happen in about 5 billion years. Perhaps it will grow to 100 or 200 times its current size, large enough to swallow Mercury and Venus. Maybe even Earth. Then, it will finally enter a different phase and eventually become a white dwarf. But Betelgeuse took a different path because it was much larger. After the main phase, Betelgeuse grew even more dramatically. Its outer layers expanded to hundreds of times its original diameter. The surface temperature dropped to about 3,000 or 4,000 Kelvin, cool for a star, which is why it glows red-orange instead of white or blue. Asterisk, meanwhile, the core continued to contract. The temperature in the core rose even higher, already exceeding the 10 million degrees required for hydrogen fusion. When it reached approximately 100 million degrees, a new reaction became possible: helium fusion. 3 helium nuclei can fuse to form a carbon nucleus. This reaction, the triple alpha process, requires far higher temperatures than hydrogen fusion, but it releases energy and can fuel the star for a time. Betelgeuse began to perform helium fusion in its core, a new stage of life. However, helium is not as efficient a fuel as hydrogen. The energy released per unit mass is lower. The timescale is shorter. While hydrogen fusion in the main sequence takes millions of years, helium fusion in the core occurs in only a fraction of that time. Asterisk, and when the helium runs out, the core shrinks again. It heats up again, and it reaches temperatures where carbon can undergo fusion. Then, when the carbon runs out, neon, then oxygen, then silicon. Each stage lasts shorter than the last. Each requires higher temperatures. Each produces less energy per unit mass. A star builds up layers like an onion, each layer fusing a different element, with the outer layers continuing to burn with previous fuels while the inner layers struggle to overcome increasingly heavier elements. Asterisk, hydrogen fusion, millions of years. Helium fusion, hundreds of thousands of years. Carbon fusion, a few thousand years. Neon fusion, about a year. Oxygen fusion, a few months. Silicon fusion, days. And then, silicon fusion produces iron, and iron marks the end. Iron is the most stable nucleus in the universe, the bottom of the energy valley, where neither fusion nor fission releases energy. Before we reach the end, let's get a little closer. In our imaginations, let's hover near the surface of Betelgeuse and look around. This experience, if you survive, will be entirely different from ordinary human experiences. First, color. From the distance we see it in the night sky. Outside the solar system, Betelgeuse appears as a single reddish-orange point of light. But if you were close enough to the star to see its disk, then you would see not a homogeneous sphere, but a surface of deep red and darker reds, rippling and boiling. Here and there you would encounter large bright regions and darker, colder spots. These are convection cells. In Betelgeuse's outer layers, hot plasma from the interior rises to the surface, radiates its energy, cools, and falls again on the same basic principle as boiling water in a pot, but on such a massive scale that the comparison is almost comical. A single convection cell on Betelgeuse could possibly be larger than the entire Sun. The star's surface is constantly covered by several of these massive structures, which rise and fall over months or years. This is one reason for Betelgeuse's pulsation. As the giant convection cells rise and fall, they cause the star's outer layers to move. When a particularly large cell comes to the surface and is pushed outward, the star brightens slightly. When it falls again, the star dims. The changes in Betelgeuse's brightness that astronomers have observed for centuries are partly due to the breathing of these giant cells. Second, winds. Betelgeuse is shedding its outer layers into space. All stars lose mass through stellar winds, which are streams of electrically charged particles that flow outward from their surfaces. Although the Sun's solar wind is invisible, it is constant and measurable, spreading throughout the entire solar system. However, Betelgeuse's mass loss makes the Sun's wind appear like a gentle breeze compared to a hurricane. Betelgeuse is perhaps losing hundreds of millions of times more mass than the Sun. During its lifetime as a red supergiant, it has released enough matter to form several suns. This matter, mostly hydrogen and helium, but with heavier elements, too, now envelops the star in a massive irregular nebula. The layered atmosphere stretches hundreds of billions of kilometers in every direction. Using the most sensitive instruments, astronomers have mapped this matter and found that it is not uniform. There are clumps, arcs, and spiral structures, evidence of jets of matter ejected by the force of large convection cells emanating from the star's surface, captured and shaped into bizarre forms by the stellar wind. When Betelgeuse's wind collides with interstellar matter, the thin gas beyond the star's direct influence, it creates a wave of arrows. This appears as a slightly curved arc far ahead of the star in the direction it travels through the galaxy. Betelgeuse is moving through space. Like everything else, it orbits the center of the Milky Way, a huge, slow circle that takes hundreds of millions of years to complete. But it also moves relative to its local stellar neighborhoods. They believe Betelgeuse was born in a different region of the galaxy and traveled through space for millions of years to reach this point. Third, darkness. If you could somehow orbit Betelgeuse the way Earth orbits the Sun at the same proportional distance, receiving the same proportional energy, you would orbit it at a distance several times greater than Neptune's distance from the Sun. From that distance, Betelgeuse would fill the sky, not like the Sun fills the sky from Earth, as a very bright disk when viewed directly, but small enough to cover with your finger. No. Viewed from a proportional orbit, Betelgeuse would fill a significant portion of your entire field of vision. Looking in any direction near it, you would only see stars. Betelgeuse's light is also different from sunlight. The Sun emits most of its energy in visible light, but also produces significant amounts in ultraviolet and infrared light. Betelgeuse, because its surface is cooler, emits most of its energy in infrared light long wavelengths invisible to the human eye. The visible light it emits is predominantly at the red end of the spectrum, which is why it appears orange-red to us. If you could see its infrared light, Betelgeuse would be even more spectacular. The star shines in infrared light. Fourth, age. Betelgeuse is approximately 8 to 10 million years old. That seems like a long time, almost 100 times longer than the entire history of the Homo species. But on a cosmic scale, it's like a blink of an eye. Our own Sun is almost 5 times older. The universe itself is 14 billion years old. Despite all its immense power, Despite the shocking energy it has released throughout its lifetime, Betelgeuse is a young star. A bright, careless, wasteful young star. It is consuming its legacy so quickly that it surprises even its more modest neighbors. And it is almost running out of fuel. Towards the end of 2019 and the beginning of 2020. An event occurred on Betelgeuse that thrilled the astronomy world and received rare attention from the general public. Betelgeuse dimmed. It dimmed dramatically. In February 2020, it dropped to its lowest brightness recorded in over a century of systematic observations. It lost its place among the 10 brightest stars in the sky and fell behind even the 20 brightest stars. Observers with keen eyes could tell that something was wrong. Orion's familiar orange shoulder, Betelgeuse, had faded. Many studies were published in the astronomy community. Theories were put forward and debated. Was this the beginning of the end? Was Betelgeuse preparing for an explosion? Had the instability following the core collapse finally begun? The answer, ultimately, was no, but the fact was almost as intriguing. The event was this. A massive convection cell on Betelgeuse's surface ejected a huge amount of matter. Billions of times more matter than a typical solar wind from our Sun was ejected in a single event. This matter-hot plasma moved outward from the star's surface. As it moved away from the intense heat of the star's vicinity, it cooled. As it cooled, its molecules turned into dustiny solid particles made of carbon and silicate components. And this dust blocked the light. A newly formed dust cloud lay between Betelgeuse and Earth, obscuring a portion of the star's disk and causing the dramatic dimming that observers witnessed. Astronomers named this event the Last Great Dimming, and analyzers using multiple space telescopes have allowed them to reconstruct what happened in detail. Asterisk, the event was reminiscent of several things at once. First, Betelgeuse is a dynamic, active, and unstable star in its later life. Ultimately, the intensity of the eruption that led to the Great Dimming the energy required to eject. So much material with such force was enormous. The star wasn't just sitting quietly. Secondly, despite all the advanced tools of modern astronomy, we cannot precisely predict when Betelgeuse will explode, nor can we confirm that an explosion is imminent. In astronomical terms, imminent can mean anything from tomorrow to 100,000 years from now. The star's behavior gives us clues, but these clues are vague. Thirdly, people are deeply affected when they learn that a bright star nearby is about to explode. The Last Great Dimming made headlines worldwide. Photos of Orion circulated on social media with impressive captions. People who hadn't looked at the sky for years went out at night to check that famous shoulder of the hunter to find its familiar pattern. Something within us reacts to the stars. This has always been present in every era of human cultures. In all civilizations that have looked at the sky and tried to understand what they saw, stars are not important to us in a practical sense, because they are so far away and we cannot directly influence them. Yet we look at them. We give them names. We tell stories about them. We feel something when we learn that one is dying. This is not foolishness. Perhaps it is one of the most beautiful things about us. Asterisk, a thought worth pondering before falling asleep. The light from Betelgeuse that reaches your eyes right now, the pale red-orange glow you might find on Orion on a clear winter night, emanated from the star. Approximately 700 years ago, the Black Death was beginning its journey across Europe. In China, the final years of the Yuan dynasty were taking shape. In the Americas, great civilizations were being built. Trade was taking place, and complex astronomical traditions were being maintained. Dante Alighieri had recently finished the Divine Comedy. Ibn Battuta had begun his voyages around the known world. All these events were unfolding under the veil of light receding from the surface of Betelgeuse at the very moment your light reaches it. The star you see in the sky is not as it is now, but as it was in the past. An image from 700 years ago continues its journey to reach you. This is true for every star you have ever looked at. The night sky isn't a snapshot of the present, it presents a mosaic of different moments in the past. Each star displaying its appearance at a different time, depending on its distance. Some stars you see may be images from just a few years ago, others hundreds of years ago, and some tens of thousands of years ago. the Andromeda Galaxy, appearing as a faint speck of light when observed on a very dark night, shows what it was like 2.5 million years ago, before our species, before the emergence of humankind, before the last ice age, before the human brain as we know it. The sky is like a time machine. Whenever you look up, you're constantly glimpsing the past. This means something significant, especially in relation to Betelgeuse. It's theoretically possible, but it seems unlikely. Perhaps Betelgeuse has already exploded. Its iron core may have already collapsed. The supernova process may have already begun, and the light from that explosion may be traveling toward us right now, at the speed of light, but it will still be hundreds of years away. We have no idea about this. Here, in the quiet darkness, in a peaceful and familiar future, the wave of light, a calling, an immense flood of light and radiation, may be moving right now. It's not threatening. 700 light-years away, it's not dangerous. But it's coming. When Betelgeuse arrives, it will briefly be brighter than a full moon. It will be visible during the day. At night, it will cast shadows. For several weeks, it will be the brightest object in the sky after the sun. People will stand on sidewalks and point at it. Media outlets will interrupt their normal broadcasts. Children will ask their parents what the bright light is, and their parents will have to decide how to explain that a star has died, or maybe it hasn't happened yet. Maybe Betelgeuse is still there, continuing to burn, flicker, and shed its outer layers into the darkness. Maybe it will continue to do so for another 100,000 years. We don't know. We can't know. We can only watch, wait, and look at the sky with patient curiosity, which is always one of our best qualities. Let's imagine this. Now, let's imagine we're there at the moment the event occurs. We're not on Earth. We can't be there for this part. We're still here, in space, near Betelgeuse, floating in what we imagine an impossible safety. Let's observe. It all begins at the core. For days, the silicon at the core has been coalescing, forming iron. Iron accumulates. For a short time, an equilibrium is established. The energy from the silicon coalescence pushes outwards from the iron core, while gravity balances the inward pull. But the iron core grows. More and more iron is added to it with each passing second. The mass of the iron core increases toward a critical threshold. When the iron core reaches about 1.5 times the mass of the Sun, this value is known as the Chandrasekhar limit. An extraordinary event occurs. The core becomes unable to support itself. The electrons in the core were constantly exerting pressure. Electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same quantum state. This provided resistance to compression, even when the temperature pressure was insufficient. However, once this mass is reached, even the electron degeneracy pressure becomes insufficient. In an instant within milliseconds, microseconds, the nucleus begins to collapse. Protons and electrons compress together, forming neutrons and neutrinos. The nucleus, roughly the size of Earth, transforms into a neutron ball about 20 kilometers in diameter. The density of this object is indescribable. A teaspoon of its material would weigh billions of tons on Earth. Gravity at the surface is so strong that the escape velocity approaches a significant fraction of the speed of light. As the nucleus collapses into this ultra-dense neutron state, it bounces back ejected outwards. Neutron matter has its own resistance to compression, and when collapsing matter strikes it, it bounces back outwards. A shockwave propagates outwards from the nucleus. Meanwhile, neutrinos countless, an almost inconceivable quantity formed during the collapse, are emitted outwards from the nucleus. Neutrinos interact with matter quite weakly. Under normal conditions, a neutrino would not stop while traveling through solid lead for a life. However, during the collapse, the outer layers are so dense that even neutrinos interact with them only slightly. The neutrino stream leaves only a tiny amount of energy in the falling matter. That tiny amount of energy is enough. The combined effect of the shockwave and the neutrino energy accumulation reverses the inward fall, pushing the star outwards. The star's outer layers, hydrogen, helium, carbon, oxygen, and heavier elements spread over hundreds of millions of kilometers are pushed outwards. Asterisk, this explosion is called a core collapse supernova. The energy released during the core collapse, just the core, in just those few milliseconds, is roughly equivalent to the total energy our Sun emits over its 10 billion year lifespan, and a large portion of this energy is transmitted via neutrinos, the light of the explosion, the enormous flare that makes Betelgeuse visible from Earth during the day represents only about 1% of the total energy released. The shock wave ejects from the star's interior at a fraction of the speed of light. Layer by layer, it reaches the star's outer shells and tears them apart. The star disintegrates from the inside out. The matter accumulated in the layers outside the core: helium, carbon, oxygen, neon, silicon, and iron, all like layers of onions ejected into space. At the temperatures generated by the explosion, nuclear reactions produce elements heavier than iron elements that cannot be created by normal fusion processes within stars. Gold is formed, platinum, uranium, lead. The heavy elements of the periodic table, these make up your jewelry. The weights on car wheels, the fuel rods in nuclear power plants, are created in the force of supernova explosions and scattered throughout the galaxy. Asterisk, the eruption expands. The shockwave spreads through the vast cloud of matter that Betelgeuse has emitted over hundreds of thousands of years. It licks at that matter, ionizing it and causing it to glow. What was once a faint diffuse cloud of gas around a dying star becomes a bright, expanding shell of plasma supernova remnant. Over the centuries, this remnant will expand, cool, and thin out, eventually becoming a very faint cloud of gas, barely distinguishable from the background. The iron core, at the center now, a neutron star, or, if the original star was large enough, a black hole will simply spin in the space where Betelgeuse once shone. Asterisk, and the light from all of this will reach Earth. It will manifest itself as a glow in the sky. Perhaps it will appear as a new star out of nowhere, because, depending on the stage of the explosion and the amount of dust in its path, the first wave of light may arrive before astronomers receive any further warning. Or, it may arrive as Earth's neutrino detectors, large buried water tanks originally designed to detect rare neutrinos from the Sun, capture the flood of neutrinos from the core collapse, traveling at near light speed and interacting only weakly with the matter they pass through. These neutrinos arrive on Earth hours before visible light. Asterisk, the detectors will sound the alarm. Astronomers will be notified. For several hours they will watch the sky anxiously, knowing what is coming, their instruments ready, and then the light will come. Asterisk, after a supernova, the universe moves on. It always does. Betelgeuse's neutron star, with its core remaining in place, is a unique object. It's about 20 kilometers in diameter, close to the size of a large city on Earth. It contains 1.5 times the mass of our Sun. It's so dense that a single cubic centimeter of its matter weighs about 100 million tons. Asterisk, it's spinning. As the core collapsed, it retained the angular momentum of the larger star. Just as a figure skater spins faster when they pull their arms inward, the collapse from something the size of Earth to the size of a city reaches incredible cyclical speeds. Newly formed neutron stars can spin hundreds of times per second. As they continue to spin, if the magnetic field is correctly oriented, neutron stars emit beams of electromagnetic radiation from their poles, like a cosmic lighthouse. If Earth is in the path of these beams, we can detect it as a regular rhythm of radio waves or X-ray waves. This type of object is called a pulsar. Asterisk. The most famous pulsar we know is at the center of the Crab Nebula, a supernova remnant observed from Earth in 1054. Chinese astronomers recorded it. Arab astronomers also recorded it. For 23 days it was visible even during the day. The nebula it left behind is still expanding today, a beautiful, shimmering tangle of gas threads that we can see with a modest telescope. And at its center, there is a small neutron star that still rotates 30 times every second. Asterisk, this is the future of Betelgeuse, not its glowing daytime visibility, not a spectacular few weeks of light show. These are the opening moments of a story that will last for tens of thousands of years. The nebula, fading, slowly dispersing into the interstellar medium, and in the midst of it, there is something impossibly dense, impossibly fast-spinning, impossibly strange. Asterisk, but let's not forget the other legacy. The matter ejected during the supernova, all that hydrogen, helium, carbon, oxygen, iron, gold, and uranium, will join the interstellar medium. It will drift and disperse for millions of years. Perhaps it will eventually reach a molecular cloud. That cloud may then collapse and give rise to new stars. These stars may have planets. Somewhere on those planets, the raw materials necessary for the chemistry that forms the basis of life can be found: heavy elements, carbon, oxygen, nitrogen, iron, phosphorus, calcium, potassium, and sulfur. This isn't an analogy or a fancy phrase. That's just how it works. The carbon atoms in your body didn't form in the Big Bang. Hydrogen formed, helium formed, but carbon is necessary inside a star. The iron in your blood doesn't come from just a star, but from the excrement of a supernova explosion. You are, quite concretely and measurably, made of the remnants of stars that exploded long before our sun. When Betelgeuse explodes, it will scatter the products of its long life into a local region of the galaxy. And billions of years later, somewhere, there's a chance these materials will become part of a planet. They could be part of an ocean. They could belong to a creature gazing at the sky and questioning the stars. We won't see it there. But this process continues uninterrupted. It existed before us. It will continue after us. We are a part of it. Dear Sir, Madam, as we slowly make our way home, it is important to take a few minutes to consider the concept of time. The human mind is not designed to comprehend the timescales required for the evolution of stars. We think in terms of hours, days, years, and generations. A human lifespan 70, 80, perhaps even 100 years is a length of time that we often struggle to grasp. History, stretching back to the 5,000 years ago, when the first writing systems appeared, is quite difficult to concretize. Our Sun formed approximately 4.5 billion years ago. It will exist for another 4.5 billion years, and then it will enter the red giant phase. The entire history of human civilization, from the first cities to the last satellite, if there is one, may be less than 10,000 years. That's about 1/450,000th of the Sun's remaining lifespan. In comparison, Betelgeuse is undergoing rapid change. Born approximately 8 or 10 million years ago, which seems like a considerable amount of time, it's only about 2% of the Sun's age, and it's already dying. In terms of cosmic time, Betelgeuse is like a fleeting light shining in the sky, bright and short-lived. Small red dwarf stars, however, will continue to burn even when the universe reaches 100 billion years old. When the Sun expands and cools, when it fades, it will have already disappeared. Even when the Earth is gone, when every civilization that lived on it has vanished from the pages of history, small stars will patiently continue to burn hydrogen, having consumed only a tiny fraction of their enormous reserves. The universe is progressing in a timescale that we can define mathematically but cannot perceive. And yet, here you are, in this particular moment, in this particular second. You take this particular breath, in this darkness, and from here, right now, you can look at a point of light 700 light-years away and understand what that light means. You can truly understand it, not just know the words, but feel an impending insight. A star 20 times heavier than the Sun, 4 trillion kilometers away, 100,000 times brighter, on a scale large enough to fit within our inner solar system. A pulsating, breathing star, shedding its layers, cooking its last elements, and approaching a moment of dreadful collapse. And you can see it with your naked eyes. On a clear winter night, there's something extraordinary about it, something worth contemplating. The universe is vast, cold, mostly empty, and utterly indifferent to human concerns. It doesn't care about us. It doesn't know we're here. We have no connection to the forces that will kill Betelgeuse, and those forces will proceed exactly as planned, regardless of whether there are conscious beings observing. And yet we are here. We are watching. Through centuries of patient study, we have managed to understand what those points of light are, how they work, and what is happening within them. We have developed instruments to see in wavelengths our eyes cannot perceive. We have developed mathematical expressions to describe processes that no human can directly observe. From fragments of light from journeys spanning hundreds of years, we have constructed the biography of a star. This is extraordinary. Whatever you think about human civilization, despite the criticisms, the embarrassing things, the hopeful situations, and the beauties, it is truly remarkable that we have been able to understand how stars work from this distance, with our minds and observational tools, and the fact that this makes you feel something, a mixture of awe, insignificance, expansion, and peace is something good about you. The universe isn't interested in you, but you are interested in the universe. Now, we gently begin our return journey. Behind us, Betelgeuse still shines. 700 light-years away, still pulsating, still breathing, still within a vast cloud of matter. It is uncertain when it will explode in our lifetimes. In our children's lifetimes, or in 10,000 years, it is impossible to say for sure. But it exists. Tomorrow night it will be there, the night after that. And the night after that, a pale orange-red dot, patiently appearing in the winter sky on the hunter's shoulder. We are lost among the stars. Each nearby star follows its own story, lives its own life at its own pace. We pass by systems we don't know, where planets may be aware of us, seasons may change, and life may exist. We return to our own solar system. Detic, deep blue and distant. Then Uranus, slanted and strange. Then Saturn, and those impossible rings. Then the giant Jupiter, with its banded structure, the asteroid belt, slow rotating rocks. And then, before us, something small and blue. Earth. From here, it's tiny. You've seen the photos. The famous pale blue dot image, taken by the Voyager probe from beyond Neptune's orbit, where Earth is a single pixel, a barely visible point in a beam of light. From a few light minutes away, it's still small, but its color is clearly discernible. It's blue. That particular deep ocean blue hue, shimmering with white clouds, surrounded by the brown and green edges of continents. You're approaching it. The continents are becoming clearer. Weather systems are becoming visible. On that surface, in a small, quiet, and comfortable place, there you are. You, lying silently in the darkness. You, breathing slowly. You, perhaps still, with your eyes closed, your body relaxed, your mind pensive. You traveled 700 light-years and returned. You stood beside a dying star and felt its magnitude. Iron cores, nuclear fusion, neutrons. A different chapter, a different dimension, but it's the same story. Stars burn, making fusion possible as gravity compresses them. Eventually, they die when they've exhausted their fuel. The elements they create are scattered throughout the galaxy, collected by collapsing clouds to form new stars and planets. And on some of those planets, under the right conditions, those elements form structures that look like them, staring out at the sky. You are a condensation of stardust, and you've learned to think stardust. That's not insignificant. In fact, it's extraordinary. Let your thoughts flow freely now. You don't need to hold on to any of them. The evolution of stars, nuclear physics, the incomprehensible distances, let it all slowly fade away, just as a supernova remnant dissipates over thousands of years. It doesn't need to stay together. It doesn't need to be meaningful in a simple, portable form. It just needed to flow through you, and it did. What remains from this whole journey is something quieter. A sense of darkness. Not frightening, comforting darkness. The same darkness that surrounds every star in the universe. The same darkness that surrounds Betelgeuse, making long bursts of light. The darkness that surrounds neutron stars spinning in their ancient ruins. The darkness isn't empty. It's filled with things we don't see. Filled with gas, dust, and photons from distant sources. Filled with that faint glow left over from the Big Bang. Filling every cubic centimeter of space with a temperature almost above zero. Your body knows how to stop. You've practiced it your whole life, every night, every sleep, every moment of rest. The systems that keep you alive work without needing your attention, effort, or awareness. Your heart beats. Your lungs breathe. Your cells do their job. You're already very good at that. Now feel the weight of your body. The comfortable pressure of the surface supporting you. The light weight on your arms, your legs, your hands, each breath a little slower than the last. The stars are still there. Betelgeuse is still there. 700 light-years away, the giant red star is still shooting in the darkness, still releasing its layers into the void, still cooking its last elements in its swollen, ancient interior. The universe is in no hurry. It doesn't rush. The stars have their time. Processes that will take thousands of years are just beginning. Events that will take millions of years are still in their infancy. You have nowhere to go. All that's happening right now is slowly drifting off to sleep. The thinking mind slowly calming down, descending into that other state, the restful, necessary, healing state your body has been waiting for all day. This state, in its small form, is a kind of journey, moving through an inner space, glimpsing places that don't exist in the ordinary world. Soften your thoughts. Allow them to be less insistent. Let them come and go, without trying to seize them. The image of the giant, ancient red star shooting in the darkness, the thought of the light that traveled 700 years to reach your eyes, the idea of the sun-sized convection cells rising and falling on the surface of the dying giant, the iron core, growing, reaching its limit, collapsing the neutron star in the ruins, like a lighthouse on the shore of a sea. Atoms scattering, drifting, traveling toward the clouds, towards new suns, to new worlds, to you. Let it all be soft and distant, like a voice from afar, like the memory of a dream beginning to fade. You are exactly where you are. The universe is in its usual place. Everything is as it should be. The darkness is comfortable. The darkness is full. The darkness is the same darkness that was here before the first star shone, and will be here when the last star dims. And within you, right now, you are breathing. Slowly, regularly, you are gliding. Good night. Betelgeuse is a real star, and much of what is stated in this account is based on current astronomical knowledge. It is a red supergiant located in the Orion constellation, approximately 700 light-years from Earth. It is one of the largest known stars, with an estimated diameter between 700 and 1,000 times that of the Sun. It is between 8 and 10 million years old and is in the final stages of its life. Astronomers believe it will explode as a Type II core collapse supernova, and this event is predicted to occur within the next 100,000 years. Although this prediction carries significant uncertainties, the 2019 to 2020 Big Dark event was a real event and is now understood to have been caused by a surface mass ejection that created a dust cloud obscuring part of the star. This was determined by analysis from the Hubble Space Telescope, the Very Large Telescope in Chile, and other instruments. When Betelgeuse finally explodes, it will not pose a threat to life on Earth. At 700 light-years away, the supernova will be spectacular but harmless. A glowing object in the sky, but not a threat. The lethal radius of the supernova for complex life is estimated to be around 25 to 50 light. Betelgeuse is identified by these processes. Stellar nucleosynthesis. The processes within stars. Geri Bildorum, Gander, Tam Severia, Germach, Echinoclary, Colonin. Betelgeuse is a real star, and much of what is described here is supported by current astronomical knowledge. This star is a red supergiant located in the Orion constellation, approximately 700 light-years from Earth. It is one of the largest known stars, with an estimated diameter of between 700 and 1,000 times that of the Sun. Its age is between 8 and 10 million years, and it is in the final stages of its stellar life cycle. Astronomers believe it will explode as a Type II core collapse supernova within the next 100,000 years. However, this prediction carries significant uncertainty. The Great Darkness event of 2019 to 2020 did indeed occur, and it is now known to have been caused by a dust cloud resulting from surface mass ejection obscuring part of the star. This was determined through analyses using the Hubble Space Telescope, the Very Large Telescope in Chile, and other instruments. When Betelgeuse explodes, it will pose no threat to life on Earth. Because it's 700 light-years away, the supernova will be impressive, but it will appear as a harmless celestial object, a shining object in the sky, but not a threat. The lethal effect of a supernova on complex life is estimated to be around 25 to 50 light-years away. The processes mentioned the formation of heavy elements inside stars, the production of heavy elements by supernova, and the recycling of stellar material into new generations of stars and planets are well-known astronomical principles. The iron, calcium, phosphorus, and other heavy elements in your body were indeed created in stars and supernova that existed before our Sun. The universe is truly as strange and beautiful as it's described. Look up sometime. Betelgeuse is a real star, and almost everything in this account is based on current astronomical understanding. This star is a red supergiant located in the Orion constellation, approximately 700 light-years from Earth. It is one of the largest known stars, with an estimated diameter between 700 and 1,000 times that of the Sun. Its age is between 8 and 10 million years, and it is in the final stages of its stellar life. Astronomers believe it will explode as a Type II quark-collapse supernova within 100,000 years. Although this prediction contains considerable uncertainty. The Big Dark event of 2019 to 2020 was a real occurrence, and it appears to have resulted from a surface mass ejection that created a dust cloud covering part of the star. This was determined through analysis using the Hubble Space Telescope, the Very Large Telescope in Chile, and other instruments. When Betelgeuse explodes, it will not pose any threat to life on Earth. At a distance of 700 light-years, while the supernova is impressive, it is harmless. It will shine as a bright object in the sky, but it will not pose a threat. The lethal effect of a supernova on complex life is estimated to be around 25 to 50 light-years away. The processes described, the production of heavy elements within stars and their recycle in supernova, are well-known topics in astrophysics. The iron, calcium, phosphorus, and other heavy elements in your body were indeed formed thanks to stars and supernova that existed before the Sun. The universe is truly as strange and beautiful as it is described. Look up at the sky for a moment. There is nothing left to do. The journey is over. The star is left behind, 700 light-years away, displaying its patient amber glow in the winter sky. Neutron stars revolve over the remnants of the past. As the discarded gas clouds disperse in the darkness, they carry loads of iron, gold, and carbon toward the future, but they will never know. And you are here? Just here. Just here. There is a special silence in the minutes before sleep. Takes you a silence different from ordinary silence. Ordinary silence is simply the absence of sound, but this silence, the silence before sleep, is an existence. It's a warm presence. It has a texture. It's the stillness of a mind beginning to let go of the day's burden, loosening the tight grip on all the thoughts and worries it's carried since morning. Notice that silence now. Gently direct your attention to your breath. There's no need to change it. You don't need to breathe in a specific way. Just observe the breath coming in and out. Feel your chest or abdomen rise slightly as you inhale. Release slowly and gently as you exhale. Each breath is a complete cycle. It has a beginning, a middle, an end. It starts again. Your body has been doing this all day without your attention. It will continue to do so throughout the night. It doesn't need you to control it. Let it go. Lower your attention downwards, away from surface thoughts, mental noise, toward your body. To the feeling of weight. To the feeling of warmth as you make contact with the surface beneath you. If you're lying down, feel the back of your head on the pillow. There's a slight pressure there, a gentle meeting of weight and surface. Feel the backs of your shoulders. Your shoulder girdles are slightly rounded toward the surface beneath them. Feel the long curve of your back as you rest. Your lower back, the backs of your thighs, calves, and heels. Every point of contact, just notice it. Just feel it. You are being held, not emotionally, physically. The surface beneath you is pushing back with full force, preventing you from going deeper. Gravity is pulling you down. The bed, couch, or floor is counteracting by raising you. You are in a state of equilibrium, resting equilibrium, like a star. A star is in equilibrium during its main alignment phase. The inward pull of its own gravity is balanced by the outward push of its nuclear fire. This equilibrium can last for billions of years. It is extremely stable, and now you have found your own equilibrium, gravity and the surface. Breathing, the firing of neurons and the quiet spaces between them. Rest in equilibrium. Allow your face to relax. If there's any tension in your forehead, around your eyes, or in your chin, release it. You don't need those muscles right now. They've worked enough today. Let them remain soft. Keep your hands soft. If your fingers are bent, straighten them. Keep your palms open, or whatever position they're in. Let your feet be heavy. The thoughtful mind wants to keep going. That's its function. It produces thoughts because that's its job, and it's quite competent at it. It just doesn't always know when to stop. Thoughts will come. That's okay. They can come. You don't need to be caught up in them. Imagine each thought as a piece of a star breaking away. It forms, it moves, it drifts away. You don't need to catch it. You don't need to examine it either. Just watch it drift away into the darkness and return to your breath, your weight, your silence. Somewhere out there, Betelgeuse is beating. Right now, at this very moment. That massive star is growing, slowly its outer layers, moving hundreds of kilometers outward under the slow influence of a convection cell larger than the sun. Tomorrow, it will shrink a little. Next year, it will shine again and again. Each shine will be part of a cycle of swelling and dimming, each cycle slightly different from the last. It has been doing this for thousands of years. It will do it for thousands more, or everything will change when it reaches its iron core limit. But not this moment. This moment is just a shine, a breath, the slow and patient oscillation of something massive and ancient, living out its own nature. And you are breathing too. Your breath is not the breath of a supergiant star. You are not someone turning silicon into iron. You are a small, warm creature in the darkness. Your lungs are expanding, your lungs are opening. In, out, in, out. But you are made of the same stuff. The iron in your blood was formed in a supernova explosion. The calcium in your bones was produced in the core of a star. The oxygen you breathe right now, the oxygen your lungs draw from the air, and your blood carries to every cell was created by the oxygen burning of massive stars that died long ago. You are not separate from this story. You are a part of it. A small, temporary, conscious, breathing part of it. And right now, your part of the story is to rest. The universe has existed for about 14 billion years, and it will continue for even longer. There's nothing currently captivating your interest. The Earth continues to spin at its usual speed. The Moon continues to move in its orbit, which it has maintained for billions of years. The Sun remains as calm as it has for 4.5 billion years, consolidating hydrogen at its core. Everything is fine. Nothing is preventing you from sleeping. Transform your thoughts into images. Loose, unconnected, undulating images. A star slowly growing in the darkness. Saturn's rings capturing light. The pale blue arcs of Earth's atmosphere. The darkness between galaxies, difficult to describe, patiently waiting. Let the images become more indistinct. Let their edges be softer. Shapeless colors. Warmth, without a source. Your breathing is now very slow. Each exhale is slightly longer than the last. Each inhale becomes easier. The body is in deep relaxation. The mind softens. The dense world of thoughts, plans, and memories gradually fades. Like a faint star, in the distance, first a single point of light, then a blurry speck, then something invisible in the darkness. The darkness is peaceful. The darkness is full of sleeping things. Every night, all over the world, all kinds of creatures retreat to rest. Birds tuck their heads under their wings. Whales slow their enormous bodies and glide across the surface, taking long, calm breaths. Bears breathe slowly in their winter dens. Small, warm mammals curl up in their burrows. The entire living surface of the planet breathes, sleeps, and dreams in the darkness, slowly turning throughout the night. And above all of them, above Uther, stars shine. Orion is either rising or setting, or, depending on the season and time, it crosses the meridian. But somewhere in the sky, the hunter is always there. With its belt of 3 bright stars, its blue-white foot, and its orange-red shoulder. That shoulder gleams. After a journey of 700 years, the light still reaches us. It still filters down through the atmosphere. It still touches the earth. It still touches you, in a very real way, whether your eyes are open or closed. The universe doesn't stop while you sleep. It rotates, burns, and expands as usual, following the laws that have governed it since its first moment. Betelgeuse will shine through the night. Neutron stars will spin. Molecular clouds will drift. Galaxies will turn with slow, majestic patience, and you will sleep. Deep, peaceful, and complete. Your body will repair itself. Your brain will consolidate what it learned today, quietly processing the day's experiences, settling some things while allowing others to dissolve. Your muscles will completely relax, far more than they ever could while awake. Your heart rate will slow. Your blood pressure will drop slightly. Your body temperature will decrease by 0.5 degree. All of this is happening. All of this has already begun. You're already on your way. As you drift into the depths of sleep, there comes a moment when thoughts cease to make sense. A sentence begins logically, then veers off the path logic would take, and you continue following it without realizing it. When images become both stranger and more vivid, when you lose track of where you are in the narrative, that moment is very near. Let it come. Don't try to reach it. Don't try to wait long enough to hold on to consciousness. Just let the current carry you. The current is gentle. The current has carried you every night of your life and has never failed. Breathe out. The star is there. The darkness is here. You are exactly where you need to be. Good night. Sweet dreams.